Assalamualaikum and hi. My name is Syakir Shafiq and our team has designed a rooftop grid connected solar PV system. And for our selection of solar panel, we have select Jinko solar panel model JKM440N. It's a Type M monocrystalline panel with a power rating of 440 watt and efficiency of 22.02%. The panel size is about 1.998 square meters and the market price is around 475 per module. We specifically choose the Type M monocrystalline panel because it offers better performance in high temperature and less light-induced degradation compared to the traditional Type P panels. This means it maintains its efficiency better over time, which is ideal for long-term energy production, especially in hot climates like Malaysia. For the inverters, we selected the GrowWatt Max 60 KTL3 LV, a 60 kilowatt three-phase grade type inverter. It can handle up to 78 kilowatt of DC input with 6 MPPT trackers supporting 2 strings each. This inverter has a high efficiency of 98.8% and its price is around 40,700 ringgit Malaysia. We plan to use 3 units of this model with the total of 254 kilowatt peak of DC capacity. And for the total usable area, we come across the rooftop with around 832.55 square millimeters. And when we account for the 15-degree tilt of the roof, it becomes 861.88 square meters. The rooftop are divided into 3 sections, A, B, and C, as shown in the layout here. Next, for the system layout, I will pass to Encik Fazli.
Hi, my name is Mohd Fazli. I'll be explaining about the system layout. So this is the general looking of our system layout. So the total number of solar panels can be installed is 328 and is separated into 3 separated roofs, which the left side on the top corner, which is roof C, that consists of 100 panels, and on the right side, which is roof B, consists of 84 panels, and on the bottom side, which is roof A, consists of 144 panels. So this total system panels can generate estimate annual energy around 212,473 kilowatt hour per year. So in terms of mounting, the system utilize fixed tilt racking system that are aligned with the existing roof slope, which is 15 degrees. And for the design consideration, adequate spacing of 0.5 meters is maintained between rows to provide walkways for maintenance access. So that's all. Next.
Hello, good afternoon everyone. My name is Lutfi Hadi. In this segment, I will present the assumptions underlying the energy yield simulation and estimation cost for both CapEx and operational management. These values will be used in financial calculation to find ROI, return of value, and payback period for our proposed rooftop solar PV systems. As you can see, to estimate the system's annual energy output, we employed the PV Watts calculator developed by NREL, which stands for National Renewable Energy Laboratory, based on the simulation and settings input shown at the right side of the table. The average daily solar irradiation at our site is 4.73 kilowatt hours per square meter per day, and assume totals and project annual AC energy output of to have almost 200,000 kilowatt hours when rounded off on the right side of the table. This simulated annual energy yield serves as the foundational input for our financial analysis. So let us now turn to the capital expenses list required for the rooftop PV system. The total estimated CapEx amounts to a total of 281,232 ringgit 80 cents and is categorized into equipment costs, installation costs, and other associated expenses. Next, for operation and maintenance costs, we have estimated an annual expenditure of 5,240 ringgit, and the highlighted cost as shown in the screen shows that monitoring system support and administrative and has the highest cost because monitoring system plays a critical role in ensuring continuous performance, tracking, and early detection of faults. Meanwhile, for administrative, focus on reporting, record keeping, all of which are necessary for regulatory compliance and smooth operational of the system. Although the PV system generally require minimal maintenance, incorporating this cost ensures greater accuracy in long-term financial projections. These operational and maintenance expenses, when considered alongside capex, form the basis for our 25-year financial model, which will be elaborated upon the subsequent section. Next, I will let Mr. Ungku to present financial analysis for IRR payback period and ROI.
Hello, my name is Ungku Muhammad Kamal Haziq, and I will continue about the energy yield of the solar PV system. From the first table here, we can see that the total energy yield for 25 years was identified to be 4.6 million kilowatt hour. This output is expected to decrease by 0.4% gradually each year because of PV modules degradation, which results in the total savings for 25 years is around 2.5 million. The in-depth long-term financial assessment of the planned solar PV system presents substantial long-term prospect and attractiveness for future investors. However, usually under FIT program, the decision largely depends on individual energy usage pattern and desired financial outcome, either maximizing immediate saving or guaranteeing a stable flow of income. We projecting savings can total up to 2.15 million within 25 years, where the value is nearly double that of the revenue that totals to 1.14 derived from FIT. Thus, the usage behavior displays an important key parameter in maximizing long-term financial benefit for savings. From the second table here, we can see that the system stands to realize a cumulative return on investment ROI of 232% after 25 years, which means that the total financial gains will be more than triple the amount of the initial investment. This high ROI creates dependable annual savings resulting from FIT revenues offsetting the comparably low maintenance costs and inverter renewals. In addition, the calculated internal rate of return IRR of 8.88% exceeds the common discount rates often applied to the project analysis. Therefore, this project has earned revenues that can outweigh the capital costs, making it comparable with other energy-related ventures or big infrastructure projects. In addition, the net present value always remains positive during the entire lifespan, and the net cash inflows in a given year outweigh initial losses from year one onwards. This ongoing positive NPV supports the claim that the project will generate more economic value in the long term, despite the discounting of money with respect to its current worth. And I will pass the presentation to the economic analysis.
Hello, I am Amir Firdaus Mishazam, and I will be presenting the economic analysis for our solar panel project. Okay, for the first one, let's look at the initial investment. The total system cost is approximately 281,000 ringgit. This amount is required to pay the full upfront cost for installing the panels, including the equipment, labor, and other related expenses such as installing new wiring in the house. So the next one is, if you examine the net annual cash flow graph, you can see that once the system is operational, in other words, the moment where the system starts operating, it consistently generates about 40,000 ringgit in saving per year by reducing the electricity bill of the house. These savings are quite stable over time, which make the system financially reliable. Okay, now moving on to the next graph, which is the cumulative cash flow graph. This shows how those yearly savings accumulate over the years for a total of 25 years. Initially, the cumulative cash flow is negative because of the high upfront cost, which is the 281,000 ringgit. But as the saving adds up, the curve rises and eventually crosses the zero line. That is what we call the payback period. So to accurately calculate the payback period, we'll be using the payback period formula shown on the right side, the table on the right, and we find that the investment is fully recovered after approximately 6.75 years. In other words, from year 7 and onward, the system has essentially paid for itself, and all additional savings from that point become pure financial gain. This makes the project not only environmental beneficial but also economically viable in the long run. Okay, next I will pass on to Azmi.
Okay, thank you, Mr. Fizaus. My name is Muhammad Azmi. Now I will present about sustainability. We use three SDG, which is SDG 7, 12, and 13. SDG 7 providing clean and affordable energy. SDG 12 using durable, recyclable materials, and SDG 13 taking real action on climate change. The system has a total capacity of 196.68 kilowatt peak and is expected to generate around 192,100 kilowatt hours of electricity per year. Environmentally, the system makes a big impact because Malaysia still use a lot of fossil fuels to generate electricity, which switching to solar helps reduce carbon emissions. Based on calculation, using Malaysia's emission factor, our system can cut down over 149,000 kilograms of CO2 every year and over 3.5 million kilograms across 25 years. So next we move to risk and uncertainty. To keep the system running smoothly, we considered several risks, which is roof B has some shading, so we arrange the panels carefully. To avoid major energy losses, to handle dust and dirt, we designed a 15-degree tilt for natural rain cleaning. We also use high-quality components with long warranties to reduce breakdowns. Lastly, a real-time monitoring system help us spot problems earlier and fix them fast. So to conclude, this project shows how solar energy can be reliable, eco-friendly and long-term solution. It supports Malaysia's clean energy vision and can serve as a long-term project and strong example for future rooftop solar system. So that's all from us. Thank you.